So this is from 7.3. Let's run through these. So how much time do 9th graders at Creek spend on homework? Who cares? Okay, I'm just kidding. A sample of 45 9th grade graders randomly. I sampled 45 9th graders randomly to find they spent an average of 38 minutes per night with a sample standard deviation of 8.6. 7.3, problem number 1. I wish I could tell you a page number, but there's a page number. It says review of confidence intervals. Find it? Sweet. All right. So let's put some things down. I'm going purple. It's fade to black. All right. So we have to think about our population is, I don't know, somewhere in the ballpark of 900 freshmen here. So things I know about that is 90 would be 10%. Is that okay to say we have right around 900 freshmen? We're off a little bit, I know, but 900 sounds like a pretty good rounded to number. Is that okay? All right. They tell us that because we've done this, we have an average of 38, and we have a sample standard deviation of 8.6. Okay? So what is my population of interest? 9th graders here at Cherry Creek. That should be pretty easy. That's all we're doing. Do the 3 assumptions apply? Well, they tell us they randomly selected, so we have to assume that randomness takes place. Is it independent? So we're going to sample. We tested 45 freshmen. So is 45 less than 10% of the entire population of freshmen? Yep. So check. We're good there. Is it normal distribution? Well, being we're testing more than 10 people. Does that keep flickering? Or every time I look away, I see something out of.
No, dude, you're sniffing blue too much.
Dude, I thought my secret's safe. Okay. All right, so being what we're talking about more than 30 people that we're testing here, it's normal distribution. So what is the standard error? So let's figure out the standard error. Okay, they said standard deviation, change it to error. So you're going to take 8.6, so whatever your sample standard deviation is, and we're going to divide it by the square root of 45. And that's going to give me 1.282. Okay? And what is the 99% confidence interval? So we know that E is equal to Z times the standard deviation over N. So am I able to use Z on this, or do I have to use T? And what sticks out to tell us we use Z versus T? Or T versus Z? More than 30. Being I'm talking about this being bigger than 30, then I'm going to go ahead and use the Z-score. Okay? Now, the table in the very back is going to be helpful to you. Okay? A lot of you want to go right to the Z table. Don't go there. Go to your table D, which is the second to the last page in the back. The reason why you want to go there, if we're using a Z-score, if you look at the very bottom under 1,000, there is the Z-score. The rest of it's the T table. Okay? And if we use the T table, remember we did the flow chart. If you had more than 30, go to Z. If you have less than 30, then you're using the degrees of freedom and figuring it out what's on the left side. So they're asking us to find the 99% confidence interval. So there's two things to think about. 99%, you're talking about 1% of the population's left. Each side of the tail has to be equal, so 0.5% of the population, which is 0.005. So two things you can do. You can either look at the very top for 0.005 and then go down to the Z-score, or you could look and find on the very, very bottom of that table 99%. Find 99% and go to the z-score, and you find the z-score is what? Yes, 2.576. So this is 2.576. Okay? Have I already worked this out? Yeah, it's right above. 1.282, that's a 1.
How do you know that it's 99%?
Because we want to do a 99% confidence interval, right? Yeah.
How did you find the Z?
Okay, so look on the left column, degrees of freedom. Okay, if you go all the way down, it gets to 1,000, and then right below it, it says Z. So that very last one, and then the 99%, we can either look for the 0.05 up here, or you can look at the very, very bottom for 99%. It's going to be the same thing. Okay, so if you go and do that math right there, we're going to find that our E score, our E value is going to be 3.302. So now I'm going to figure out my confidence interval. So we have 38 minus 3.302 and 38 plus 3.302. If you add those together, then this is going to give us a confidence interval of 34.698, 41.302. So it's pretty wide. So we are 99% confident that if we did our same selection of people, same population, we reduplicated our test and found another 45 people to test, we are 99% sure that our mean of that new group will fall between 34.698 and 41.302 minutes. Okay? Split. So then, what would the 80% confidence interval do? So this right now is a confidence interval, encompassing this wide of a range. That's at 99%. I'm 99% confident it's going to take place. If I was 80% confident, what would this look like? This is going to drive me nuts. Is it a smaller sliver or wider? 80%. I'm 80% sure my results are now going to take place. So that's going to actually make this be a smaller region. Okay? Because you're not as sure. You're giving up a little bit of the freedoms there. So say, okay, I'm 80%. I'm 99% sure it falls between these two values pretty far out. I'm 80% sure it's going to fall between these two values closer in. Okay? So the confidence interval would be smaller for 80%. And then if you were to do this, what is the critical score if we change our sample size to 20? So if we change to 20 people, what are we changing on our equation? Which value are we going to use? We're using the t-score. Why? Because this is less than 30. So what's my degrees of freedom then? How much? 19. So my degrees of freedom is always one less than what we're doing. So again, if we use our table, and we're still using the 99% confidence interval, and I'm going to use degrees of freedom 19. Right? I get it? So degrees of freedom is 19. Right? 99%. What'd you guys find? What is it? How much? There you go. So this is going to result in a t-score of 2.861. Notice that's different than this. Okay, why is it different? Because I was less than the 30. So my z-score is absolutely awesome to use, but if I just don't have as many people I'm selecting, this is going to change. So then you split back to it.
Wait, where
the table D. It's the second to the last page in the back of the book. That's right. It says it has a shade to the right. So 19 degrees of freedom, because degrees of freedom is always one less than our actual population, or our actual test subjects. And then what's really kind of cool here, I'm going to come show you because you're at the right page. So if I'm using a 99%, I can either go 99% down here, or I can use the 0.05. And then figure out where 19 degrees, 2.61 should be right there. But if you're using more than 30, you're just using that very bottom. If I sample more than 30 people, then don't use your degrees of freedom. Go to the z-score. Even though this goes all the way up to 1,000, there's other tests in place, but for right now, if you have 30 or less degrees of freedom, more than 30, so 31, 32, go to the z-score. Don't worry about it. Well, this has 500. I don't care. Okay? All right, so that is the z-score. So the z-score is very, very bottom of that same. Go to the very bottom column.
Oh, and then I just the very bottom column. Okay.
See, right above the percents. So theoretically, that's the only table you need to worry about using, because it's already got the z-score on it. The pages before had the z-scores as well, but that better now. All right, so E, I'm using T now over. So I'm going to go 2.861. Standard deviation of the population, 8.6 over the square root of 20. And I do that, and this is going to come out to, if you do the math right, 5.502, which means I'm going to go 38 minus 5.502, and 38 plus 5.502. And then that goes to 32.498 and 43.502. Okay? So now, if I've used less people, my confidence interval has now opened up even further. I'm still using 99%, but this was from 34 to 41, roughly. Now this is going from 32 to 43. I'm using less people, so I'm going to say, okay, now it's going to fall between much wider region because I'm using less people.
So and it is the sample size.
N is the sample size. So we did change, this was 45 as N, and now it changed to 20 because we decided to do it with a different thing.
Why
Okay.
is it T there and Z there?
Okay, the reason why it's Z here is because I'm sampling 45. I'm sampling more than 30 people. So if I do more than 30, Z. 30 or less. Do what?
No matter what the sample population is.
That it is. There's, right. As long as you, yes. There are tests that we're going to go through saying, was this random? Well, if they tell us it's random, then we got to assume it's random. Are we talking about, we have an entire population here, what's our sample? Are we talking about more than 10% of it? Then it wouldn't fall into this. If it's less than 10%, yes. And then, how many people are we talking about? Are we talking about 30 or less T-score, more than 30 Z-score? Did I get that right? Yeah, I think I said it right. I didn't see too much confusion. All right, number two. I'm just following by what the guide says. It says the filling machine at Coors Brewing Company. Sorry, we're talking about beer production here in class, but I'm just going along with what the problem says. Okay. It's supposed to fill cans of an average of 12 ounces and standard deviation 0.05. Okay? So, you have a can. This is supposed to be a 12-ounce can. In this case, we're talking about beer. Okay? So they're saying that you have an average of 12 ounces. You have a standard deviation of 0.05. Okay? A particular machine has been troublesome lately. The manager randomly samples 50 cans. So he's taking a look at 50 cans of this beer coming out of this particular machine. Okay? And he finds that they are being filled with an average. So my sample average is 11.6. Okay? So what is the population of interest? All the cans coming out of this particular brewing plant for Coors. Okay? Do the three assumptions apply? Is it random? Well, it tells he samples 50 randomly, so yes. Is it independent? Is 50 cans less than 10% of all the cans produced? I have no idea how much they produce, but I don't think 50 cans, if when the brewing line's going, the canning line's going, I don't think that's that many. No? So we're talking about less than 10% of all the cans produced. Is it normal? So we're dealing with 50 cans, and as long as we're dealing with more than 30, it's a normal distribution. Okay, what is the standard error? Okay, so let's find the standard error. So we're going to go the standard deviation over the sample. So I'm going to go 0.05 over square root of 50, and this is going to give me 0.01, or wait, no. 0.00707. James Bond going on there. Okay, what is our 95% interval for the average amount of cans filled by this machine? Okay, so I have E is equal to, I'm using Z because I'm using more than what number? 30. Standard deviation over the sample. Okay, so we want to create a 95% confidence interval. Where am I going to find this? Table D. Where at? Yeah, look to the 95, which you'll find on the very bottom. We're using the Z-score, so we're not worried about degrees of freedom. So we're talking about what? 1.960, right? So my Z-score is going to be 1.960. Did I write that correct? Times this, because we found it to be this, which is this. So 0.00707. So if I multiply those together, that's going to give me 0.0139. Okay? So what I did is I took my standard error, which is this standard error is the same thing as right here. Standard deviation over the sample size, square root of sample size, times the z-score. So 1.960 is the z-score times 0.00707. If I multiply this together, I get 0.0139. So now we know this. So we know that this particular machine is producing at 11.6. I'm going to go 11.6 ounces minus 0.0139 and 11.6 plus 0.0139. And if I do this math, I'm going to get 11.586 and 11.6139. So I am 95% confident that if I were to reduplicate this act on this machine, this is what my averages are going to be from. Do you think the manager has a worry about this machine? And the answer is yes. Why is it yes? We're trying to get 12 fluid ounces. Our confidence interval, we're 95% confident that if we duplicated this test again, we're still way under 12%. So this particular machine needs to get fixed. It's not pouring enough of the liquid into each of the cans. So anyone who's getting cans coming off that line is actually getting gypped a little bit because they're expected to be buying a 12-ounce beer, and this particular machine is not putting it out there. Is that a lawsuit? I see some yes, I see some no's. You guys, this is before your time, but in the 80s, McDonald's was sued because their quarter pounder did not weigh a quarter pound. And the people won. So if you go into McDonald's now, to the quarter pounder, you'll see a little asterisk next to it, and it says, wait before cooking. That's how much the ground beef that they're using, that patty, is going to weigh before they cook it. But McDonald's was sued. Poor McDonald's. Lady spills hot coffee on her lap. They get sued because she didn't know it was hot.
Well, it was also like way too hot. Like it melted her clothes to her skin.
I know. I've seen that. There's some graphic
It's
pictures.
gross.
Subway was sued because their foot long isn't actually.
See?
How do you stick to this? They don't even do that for $5.
$5 sandwich.
They don't do that.
Gosh. I don't know about y'all, but when I go to a restaurant, just give me the food. I'm going to eat it. I'm not going, oh, it's about an ounce or two less than what I thought it should be. Yeah, those pictures of that lady. Yeah. She might have poured hot lava down there because those are horrific. What happened? Pass some notes, All right, let's do this quiz. Guys and girls, for tomorrow, I would like you to work on 3 and 4. 3 and 4 on this, and I'll check off 1, 2, 3, and 4 tomorrow. Got it? Sound good?
Wait, you're taking a quiz?
Yeah.
What?
You'll do fine.
Wait.
You can keep those books out, though.
Oh,
Keep those books out.
Can I take this or?